learn about time and distance. And slowly we map out the world around us, the things that we become familiar with, using this idea of measurement, of comparing things. And that's exactly what has happened. And over the years, the centuries of our civilization that we have managed to keep going, we've reached out into the vast. You can see the clouds that Ian was talking about in the last talk, and into the imperceptible. We've discovered microbes and bugs and atoms, and we've reached out here, and the thing that has enabled us to do that is measurement. It's measuring things and then seeing what happens. It's enabled us to have ideas about them, but it's measurement that's at the heart of it. And that's why the key thing I want to communicate to you, that science is not about maths. So the way science is taught, it always seems to be embroiled with mathematics and complication that just puts people off, frankly. Maths is about a very specific way of working out logical consequences, a way of thinking, but science is about measurement. Okay, that's the first thing. The second thing is to tell you what measurement is. So measurement is really simple, just like with a measuring stick. It's just quantitative comparison of one thing with another thing. It's the simplest idea. Now, if you've got a standard thing that is, maybe it's your kingdom standard or your local standard, that's okay, because you can just go and compare it directly. But actually, often the standard isn't in the room with you. The standards, the measurement standards that we have are often really quite distant from us, and so you don't get to compare the thing you want to measure in your lab or in your house directly with the standard. You have to go to a copy of the standard, maybe not even a copy of the standard, maybe an extra copy of the standard. And typically, when people are measuring things in factories, they're actually using a copy of the copy of the copy of the standard, and that's what they make their measurement against. That's what they do their quantitative comparison against. And every time you make one of those things, there's a little bit of uncertainty. You can never make perfect copies. And so if you want to make a measurement in one time and place and connect it with a measurement made in another time and place, you have to have this traceability back to these standards. And each time you do that, there's an extra little bit of measurement uncertainty. But whatever you do, you can never make a measurement that's got a lower uncertainty than you have of that standard quantity. So all the measurements that we make out in the world depend on the standards that we're making comparisons against. That's the second thing. And here's the last thing. It's about precision measurement. So I've led the team at MPL that's made the most accurate temperature measurements in human history. I'm ridiculously proud of this. Oh, yes, thank you. And people come to my lab and they want to see the thermometer we used. It's quite a complicated apparatus. And they're always very polite, but they fail to hide their indifference. And I thought, how can I communicate to people that this really matters? And I realized that if I told them that I was polishing a piece of glass in order to make a lens that would show a sharper image of something, they wouldn't even ask me why I was doing it. It would be obvious that if you have a sharper image, you see things more clearly. There's less distortion in the image. That's just obviously a good thing. And that's what precision measurement is for physical science. It allows you to see the two things that appeared to be slightly different are in fact exactly the same. And things that appeared the same are slightly different. And you can ask questions. Precision measurement literally brings the physical world into sharp focus. That's why it matters. Okay, those are the three things I wanted to say before I began. We could stop there, actually. So okay, I'm catching my breath. And I want to talk to you now about the International System of Units. And I normally have a rule for talks, which is one talk, one thing. Just talk about the thing that you going to talk about? It's quite a simple rule, but I'm going to break it. Today I'm going to talk about two things. I want to talk to you about the International System of Units, but first I'd like to tell you about my system of units. So it's a system of measuring that I've invented. It goes like this. It's got a standard length. That's called a Michael. It's the standard length. It's got a standard mass. That's called a Stephanie. It's named after my wife. Now, someone did suggest to me that naming a unit of mass after my wife might not be very diplomatic, but I'd like to tell you it's a very petite unit of mass. And a standard time. That's the Maxwell. That's my son. And it's the period of a pendulum of length 1 Michael with the mass of Stephanie, and it has to be done in Teddington. And the Michael, by the way, is the length of the standard Michael at 20 degrees Christian. That's my other son. Okay, so how do we this is what measurement is, quantitative comparison. So how do we go out and make some measurements? So what we need is a copy of the standard Michael. In fact, what I have here is actually the standard Michael. It's the only one in the world. I can't put on a pair of gloves here. So this is rather precious. And here it is, the standard Michael. It is exactly 1 Michael from here to here at 20 degrees Christian. Now, of course, this is very, very precious, and if we want to make measurements out in the world, we need to have copies. So I've got copies here of the standard Michael. They're pretty good copies. Let me show you how it works. So here's the Michael, here are the copies, and what we need to do is make sure that they're all the same length. So we compare them at each end to make sure they're the same length. Obviously, I can never be absolutely sure. There's always some uncertainty of comparison, but we do the best we can. And then what we can do is we can use these copies to measure big distances in the world. We can stack them end to end, and there we have, look, that's a pentamichael. So here's a copy, and we can put these end to end like this. You get the idea. And you can do that with masses as well. Now, notice that we're using the standard Michael for two things, and this is a big problem in measurement, is that this defines what we mean by length. This thing, everything I'm going to measure in the world is in terms of this one artifact. So it's really, really precious, and I'd like to put it in a safe and leave it alone. But I can't. Because it defines the system, I've got to keep taking it out when I want to make fresh copies. So it's both defining what we mean by length, and it's the seed for the dissemination, the realization, as it's called. So let's see how we make some submultiples of a Michael, and then we'll see how to make a measurement. So here's a Michael. I mean, now we want to make halves and quarters, so we create a Mitch. Create 2 Mitches, and we check that the ends match up so that they're equal in length, and then we put the Mitches end to end and see that they add up to 1 Michael, and then we can be sure that they're a half a Mitch each, a half a Michael each. So now we can make measurements in the world. So here's an unknown length, and you can see that it's 1 Michael, put 2 Michaels together, and then 3 Michaels. Okay, let's get rid of that one, and we have a half. You see, we've made a measurement. Now, the SI actually uses this kind of thing. That's 2.875 Michaels. We've gone from this standard thing. By doing quantitative comparison, we've made measurements out in the real world. And that is how measurements actually, even in the SI, that's how they work. So we can do time as well. So we can just count Maxwell's, throw a ball up in the air, count the number of pendulum oscillations. It took 5 Maxwells. Let's just do that again. Then we go up in the air, 5 Maxwells. Now you might be thinking, that's not very accurate, because it's quite a long period in the same way that the second is quite a long time actually. But of course, we then just make a smaller pendulum, which counts decimaxwells. And that one took 52 decimaxwells, that's 5.2 Maxwells. So you can see now we can measure more and more precisely. And in fact, you know what, you can make them smaller and smaller and smaller. You can make them the size of atoms. And then you've got really, really high frequency tick-tocks to time things against. And these are the base units of my system of units. There's the Max, the Mic, and the Steph. And you can put those together to begin to measure more complicated things out in the world. So, for example, here's speed. So that ball is going to shoot across the screen, and it's going to shoot across the screen here. And when it goes past the first line, the clock will start. When it goes past the second line, the clock will stop. So here it goes. So, whoa, fantastic. 1.1 Maxwells it took. And that's 2.875 divided by 1.1 Michaels per Maxwell. Now, my system of units is very, very thorough. I've put a lot of effort into this. And so we've got abbreviations for these units, and that's called a Micamax. So, in the SI, they've got rules for, did you remember Ian said 10 to the power 14 and 10 to the minus 1? When you divide by a unit, you put minus at it. So for meters per second, they say meters second to the minus 1. I think it's really rather an ugly thing. In my system, you just put O in front of it, Micamax. I think it rolls off the tongue. I'm going to recommend it. And you can measure accelerations. So there you get speeds from each little clock stopping and starting. So we get a table of speeds, and we can work out accelerations. That's 0.413 Micamax a max. And you can work out forces. You can stretch this thing a very long way. And that is my system of units. And I want to recommend it to you. There's the Sharmila, that's the unit of force. The Andrew, that's the unit of torque. Any of you who have met Andrew will know exactly why that's the right name for the unit. And the Insyuk, which is the unit of pressure, the force, that's the number of Sharmilas per square Michael. My system of units, I hope you noticed that the names are gender balanced, and they're also ethnically diverse. But perhaps you've spotted there's something wrong with my system of units. Can anyone think of anything wrong with my system of units? Oh, damn, you've got it first time. Only I know it. That's right, no one else uses it. And you might think, well, that's very nice. But the point about systems of units is their specialized language for communication. In the same way that philosophically you can't have a private language, it's nonsensical. In the same way you can't have a private system of units. And when we use units, they're not for our convenience or for my aggrandizement. They're actually to communicate with other people. And so it needs to be a shared system to work. Now there are a couple of other weaknesses also shared with many other unit systems. The first one is that thing I put. The first one is that thing I pointed out. The standard Michael or Stephanie could get damaged, and then it might change its length or weight. And this has happened to every unit system that has been created. At some point over a few hundred years, the fundamental standard objects that have been created have been damaged, often destroyed. In the UK, the standard pounds and yards were destroyed in a House of Commons fire. So this is a real risk. The second thing is we're trying to use the units for two different things. If you've got a standard unit, like I said, you want to keep it perfect and put it in a safe. Don't touch it. but on the other hand, that stops you making copies of it. And then you think, well, you'd have a secondary standard, but then that's not the standard. It's a secondary copy. So you've got to make up your mind. There's this conflict there. And the last thing is the standard values are just completely arbitrary. Now, the reason that I have wasted 10 minutes of my precious time here to talk about my system of units is I want to communicate to you that all system of units, just like my system of units, are made up. We just make them up. We invent all those words that you're familiar with, the meter, the kilogram, the Kelvin, all these things. People have invented them for particular reasons, particular conveniences. They have a history, but they're invented by people. And that's why I use this ridiculous example. Okay. So let's get on to the International System of Units. Now, these are the base units of the International System. There are 7 of them, and we sit them round a table like this to try and show that they're somehow of the same status. They're like the United Nations. There are some that are bigger and more powerful than others. So they differ dramatically in the concepts they use for realizing the units, but there they are. And there are lots of things right with this. So the thing that's most right is that everybody uses this system of units. It is humanity's universal system of measurement. And it's in the name. The clue is in the name. It's the international system of units. It's not called MKS, it's not called the imperial system, the British system. It's the international system. And this international agreement is at the heart of how it works. Some of you might be thinking, wait a minute, don't Americans still use pounds or something like that? And you know what, since the 1960s, well, you know, they still do use pounds, but since the 1960s there have been no standard pounds. A pound is just a fixed fraction of a kilogram, and don't tell them. And again, the Fahrenheit, I hate using that word, the Fahrenheit doesn't exist separately from the degree Celsius and the Kelvin. So everyone uses the SI, but now the standard meter has been replaced by an idea, which I'll talk about, but the kilogram could still be damaged. It's still exactly like the standard Michael here. It's an artifact that could be damaged. And it could be just damaged, or more precisely, it could be corroding or changing in some way. Now, units such as the kilogram and the Kelvin still mix up this idea about being the seed of disseminating the unit and being the definition of what we mean by it. And the standard values are arbitrary, not natural. And for some of these reasons, we're going to change the definitions of 4 of the SI units. It's going to happen in May 2019, and it's coming to you. Now, let me try and explain why. So the definition of the second affects the definition of the meter, the candela, and the ampere. The definition of the meter affects the candela and the ampere, and the definition of the kilogram affects the mole and the ampere. So the kilogram here is at the heart of why we want to change the definitions of the system of units, because the kilogram is changing its mass. So the kilogram spends all its life in a safe. It's a very, very dull life. It was created at the same time as a large number of prototypes. The UK has a copy number 18 of the kilogram. That lives at MPL. And every 40 or 50 years, the kilograms from around the world assembled for a family reunion in Paris. And they're all compared to do you remember when you put your children up against a thing with the wall and how big? Oh, you've grown so big. That they do that thing with the kilograms. They compare them, and they should all be exactly the same, but they're not. They're all they're changing against the kilogram. Now the kilogram, the international prototype of the kilogram, defines what humanity means by a kilogram. So it always weighs a kilogram. It doesn't matter how much weight it puts on, it still weighs a kilogram. If only that were true for me. And so what we see is all the masses of the kilograms in the world have all changed against the prototype, the international prototype. So what we have to guess is that the international prototype itself is also changing, but we have no way, even in principle, of detecting by how much. But if you guess roughly, you'd say it's changing by 1 part in 10 billion per year. So that's about 1/10 of a microgram per year. Don't panic. It's going to be okay. But from a meteorological point of view, it's completely unsatisfactory. But if you change the definition of the kilogram, you're going to affect the definition of the mole. That's the amount of substance, how many atoms there are in things. And if you change the definition of the kilogram, you're going to change the definition of the ampere. And if you change the... oh, wait a minute, there's the Kelvin there. It's just sitting there by itself. Maybe you don't have to do anything about the Kelvin. Maybe it's fine. You know, you just change yourself, I'm fine. But the Kelvin has its own problems, and so we're going to go to work on the Kelvin as well. So let me tell you about the new international system of units and what we're trying to do. Why are we trying? I mean, did you have a problem with the old international system of units, sir? I don't think so. It's not what people knock on my door and ask. So here's measurement. It's quantitative comparison with a standard. And the question is, these standard quantities, could we define them a bit better with the hindsight we have now of the 20th century of fantastic science? Could we choose our units more wisely? So one of the things we measure with our unit systems is we measure things we think are fundamental constants of the universe. So we take kilograms, amperes and kelvins, and we measure things like the Planck constant, the elementary charge and the Boltzmann constant. And this is a bit funny because the units are our human scale standard objects, but those things on the other side, the Planck constant, we think that's a truly constant thing. As far as we can tell, it's a real constant of the world. And as our measurements improve, our estimate of the Planck constant just keeps moving around a bit. But that's wrong. It's the Planck constant that's constant. It's our measurements that are the changing thing. So what we want to do is to swap those things round. So the natural constants of the universe that we see are the basis of the system of measurement. And then we have unit definitions in terms of them, and then we use them to make the system that we use to measure normally. It's a changing concept of what a measurement unit is. Now, some of you might think, well, how do we know the constants are constant? Good question. And it turns out you can make a very good guess. You can look at the light from distant stars, and the light has come out of atoms in distant stars a long, long time ago. But you can see that the frequencies are very similar to light that comes out of the same atoms on Earth right now. And amazingly, you can do an experiment even in the lab right now that can detect very sensitively any change in the constants. This combination of constants here, called alpha, which has got a E squared over hc, that's the charge on the electron squared divided by the Planck constant divided by the speed of light. That combination of constants affects the frequencies with which atoms jiggle. If you hit an atom, it jiggles. So let me hit one there. That's an atom wobbling. And some of these wobbles depend on alpha, and some depend on alpha squared. So let's, you see that's wobbling much faster. So these are like atomic clocks where you set atoms wobbling and count the ticks. And you can set two atoms wobbling and see whether their relative frequencies changes over a year. And that's been done at MPL and at the German lab PTB. And the answer is the fundamental constants appear to be at least 1,000,000 times more stable than the kilogram. And that's astonishing. So if we were going to change the system of units to something that was 10 times better than the kilogram, that would be a useful change. The kilograms lasted 100 years. Decent bet for our civilization, according to the last speaker, is 1,000 years. 10 times should do us nicely. These constants are 1,000,000 times more constant, more stable than the kilogram. So that's the thing that motivates us. Now, what we want to do is now to separate the definition of a unit from its realization. So we want to move these things apart. So the definition is what we mean, our idea of what we mean by a unit, and the realization is how we go about making it out in the real world. Now the way we realize a unit changes over time. Think back 100 years to what a laboratory would look like. Clue, just look around you right now. It's got lots of wood and brass. And then think to a modern lab. It's clean and it's got computers and it looks completely different. The technology has changed dramatically. And what we'd like is to be able to have ideas that endure perfectly, but allow the technology in the next 100 years to evolve to give us better measurements. So this picture I drew earlier, what we want to do is take that standard and separate out its definition. And then this thing, all these steps are about realizing the unit. Then the definitions are based on the fundamental constants of nature, the things about the world that we think are truly constant. And this is about technology and about things that can get better with time. So it's going to lay the foundations for future centuries of measurement. So for the kilogram, what we want to do, there's our standard kilogram, and we're using it to measure the Planck constant. So we want to swap that round, and now we're going to use the value of the Planck constant, a definition in terms of the Planck constant, to make a kilogram. We're not going to actually make one, but we're going to be able to weigh something in terms of fundamental constants and say that's 1 kilogram, rather than just comparing a mass against the standard kilogram in a number of stages. And so there's the definition, what we mean by 1 kilogram, and the realization, how we translate it into practice. So that's the international prototype of the kilogram. That's now no longer what we mean by a kilogram. We want that to be part of how we realize it. Standard weights aren't going to go away. It's a great technology. But now what we mean is some piece of basic physics where we have a wavelength defined in terms of the Planck constant and the mass of fundamental particles and their speed. It's a fundamental definition of mass. With the ampere, currently it's defined, it has to be the worst unit definition ever. It's defined as that force which acts between two infinitely long, what? Infinitely thin parallel wires 1 meter apart in vacuum. I mean, it's a bonkers definition. But it was written that way to allow people to wind coils and have calculable forces between coils. We're going to take that definition, which we've used to measure the charge on the electron, and swap them round. So now the charge on the electron is the fundamental thing we really believe. We'll have a unit definition in terms of that, and that'll tell us how to make an ampere and how to measure it. So that definition is part of forces between coils. That's how we realize it. Now, electrical current is related to how many charged particles flow down a wire per second. That's electrical current. That's what we really mean. And the Kelvin, the unit so close to my own heart, that's defined by the temperature of the triple point of water. At the minute, we define the temperature of the triple point of water to be 273.16 Kelvin exactly. And every temperature measurement on Earth is a comparison against that temperature. Now, using the power of telepathy, I know what about 80% of you are thinking, and that's, what's a triple point? So earlier on, I made some up and brought some in, and I'll hand some out. So, Mr. Camera person, are you able to zoom in on something? Oh, yeah. So I don't know if you can you zoom in on that? About here. Excellent. So what you should be able to see is down at the bottom here is water, and around the middle here is ice, and up at the top here is not air but water vapor. And at this point right here, where liquid water, solid water and water vapor all exist in equilibrium together, that spontaneously stabilizes at humanity's standard of temperature measurement. And you'll find these things in every standard temperature lab. And this is humanity's temperature standard, the triple point of water. So I'm just going to pass these round, so do take a look. It'll be melted by the time it reaches you guys. Just to say, it's cold. Do take a look. Now, it's a lovely artifact, but it seems a little bit funny for the 21st century to me. So what we're going to do is we use that to measure the energy of molecules, how much energy per degree molecules have. So now, well, I've been working on this project for a long time, 10 years actually. We've now measured the Boltzmann constant, how much energy particles have per degree, and from May 2019 we're going to define the unit of temperature in terms of that. So this triple point cell is no longer going to define what we mean by temperature. It's no longer just be a comparison how much hotter or colder something is than that point in a triple point of water cell. What we're going to refer to now is molecular motion, and we're going to have a value of the Boltzmann constant that tells us how much energy of motion particles have, and by measuring that energy of motion we're going to be able to work out the temperature